In last lecture, we have seen division algorithm and some problems on division algorithm. Now today we shall see what is divisibility and properties of divisibility. We shall start from the definition of divisibility. Consider two integers a and b. The integer b is said to be divisible by an integer a if there exists some another integer c satisfying the condition that b is equals to a into c. Okay, then we say that the integer b is divisible by an integer a. That means integer a divides the integer b, and in this case we write like this symbol: a divides b, or b is divisible by a. If b is not divisible by a, it is denoted as like this. This is a divides b, that means b is divisible by an integer a. This a does not divide b, or it can be read as b is not divisible by a. For example, if we consider a is equals to 5, b is equals to 10, and we know that this 10 can be written as 5 into 2. That means d is equals to a into c. Here c is 2. C is 2. That means 10 is divisible by 5, or we write this as 5 divides 10. Or if you consider a is equals to 2 and b is equals to 11, then this 11 is written as 2 into 5 plus 1. That means this is the division algorithm of the form a is equals to bq plus r. Here remainder is not 0, in this case remainder is 0, therefore b is divisible by a. In this case we write 2 does not divide 11, or 11 is not divisible by 2. Okay, this is the definition of divisibility. It is similar to the division algorithm. If the remainder is 0, then there is a perfect division. That means b is divisible by a. Now we shall see the properties of divisibility. These properties is stated as the theorem. Consider a, b and c are any three integers in this theorem. Now, first property is a divides b, 1 divides a, and a divides a. First, a divides 0, this is 0, a divides 0, that means 0 is divisible by a, and already we know from school level 0 is divisible by every integer, or it can be directly follows from the definition of divisibility. Second, 1 divides a is a integer, and we know that every integer is divisible by 1. That means this is also true, 1 divides a, and a divides a means every integer is divisible by itself. In second, a divides 1 means any integer divides 1 if and only if that integer is equals to either plus 1 or minus 1, and we know that 1 is divisible by only 1 or minus 1. That means for a is equals to, or a is equals to 1, we have a divides 1. That means 1 divides 1. Or if you consider a is equals to minus 1, that means minus 1 divides minus 1. 1 is divisible by plus 1. Also 1 is divisible by minus 1. That means A divides 1. This is only possible if A is equals to either plus 1 or minus 1. Now proof of first two are very simple, which are directly follows from the definition of divisibility. Now we have proved this. It follows from definition of divisibility. Now we shall prove the third result. A divides B and C divides D. Then we have to prove that AC divides B into D. What is given? A divides B and C divides D. Now A divides B. Apply the definition of divisibility. A divides B, that means B is divisible by A and B is divisible by A if there exists some integer x here. I am taking x such that B is equals to AX for some integer x. X is a integer. Second, C divides D. That means D is equals to C into some another integer. We shall denote that integer by y. We have written these two equations by using the definition of divisibility. Now we have to prove that AC divides BD. That means BD is divisible by AC. And when BD will be divisible by AC? If there exists some integer such that BD is equals to AC into that some integer. We have to prove this. We have to prove BD is equals to AC into some another integer. Means take the product, then this implies B into D is equals to AX into CY. AX into CY. This implies B into D. As we want AC divides BD, I am writing AX into CY as A into C into XY. Okay? Now here X is an integer, Y is also integer. Then product of two integer is again a integer. Therefore X into Y is a integer. Means we have BD is equals to AC into some another integer. That means this implies AC divides BD. AC divides BD. That means this result. Okay? Try to understand meaning of this result. A divides B and C divides D. Then A into C divides B into D. For example, what is first condition? A divides B. Suppose 5 divides 10. And second, C divides D. 4 divides 16. 4 divides 16. Okay, 5 to the 10. 4 4 the 16. That means 10 is divisible by 5. 16 is divisible by 4. Then the result is B into D divides, A into C divides B into D. That is 4 into 5. This is 20 divides 10 into 16. It is 116. And is it divisible? Is 116 divisible by 20? No doubt, which is divisible by 20. You can verify 160 divided by 20. Then what is the quotient? It 28 are 160, or you can multiply 8 0 0, 8 2 16, remainder 0. That means this is a true. A divides B, C divides D implies A into C divides B into D. This is a third result. Then proof of fourth. It is given that A divides B and B divides C. One integer divides the second and second integer divides the third. Then we have to prove that A divides C. That means first integer divides the third integer. Now here fourth, A divides B. By the definition of divisibility, A divides B implies B is equals to AX for some integer X. And second, B divides C. This is a B divides C. B divides C. By the definition of divisibility, this implies C is equals to B into some another integer. C into B y or some integer y. A divides B implies B is equal to X for some integer X. And B divides C implies C is equals to By for some integer y. Okay. Now we want to prove that A divides C. That means first integer divides the third integer. When C will be divisible by A, if we are able to write that C is equals to A into some another integer. As we want to write C is equals to some another integer, from first equation put the value of B in second. That means this implies C is equals to, what is the value of B? B is AX into Y. Putting value of B from first equation in second equation, we get C is equals to AX into Y. Now this can be written as C is equals to, apply the associative property, it can be written as A into X into Y. Again here X is the integer, Y is also integer, and therefore their product X into Y is a new integer. That means here we get C is equals to A into some integer XY. As the XY is arbitrary, it can be written as A divides C. Okay? That means A divides B, B divides C implies first integer A divides third integer C. For example, 5 divides 10, 10 divides 20. This implies clearly 5 divides 20. This is true. This is a property. If one integer divides the second integer divides the third integer, then clearly first integer divides the third integer. This is an example. Or you can consider 2 divides 4, and we know that 4 divides 16, and no doubt 2 also divides the 16. Okay. Now we have proved the fourth result. Now we shall try to prove fifth result. Now try to understand meaning of this result. A divides B and B divides A. That means consider any two integer and these two integer divides each other. A divides B and B divides A. This is true if and only if A is equals to plus or minus 1. That means they must be equal with same sign or opposite sign. This is the result. Now prove. First A divides B. A divides B. Apply the definition of divisibility. This means B is equals to A into some integer. We shall denote it by X for some integer X. Second, B divides A. Reverse. B divides A. This implies a is equals to by for some integer y. Now we want to prove that this a divides b and b divides a. We have taken this part. Then using this we have to prove that a is equals to plus 1 or a is equal to plus or minus b. Now from 1 again we shall put the value of b in second. Then what we get? From 1 and 2 we have a is equals to by. But what is b? B is a into x. Put the value of b here. A into x into y. This implies a is equals to a into x into y. And this implies a is equals to a into some integer. This a is same. That means this implies x, y. What is the value of x, y? If x into y is 1, then a is equals to a. This is true. Okay? If x is equal to y, x into y is equals to 1, then this equation will be true. Otherwise it is not true. Okay? The x is an integer, y is also integer, and here product of these two integers is a 1. When this is possible, either both the integers are 1 or both the integers are minus 1. That means this implies x is equals to y is equal to plus 1 or minus 1. Both must be equal and 1, or both must be equal and minus 1. Now we shall consider first case. X is equal to y is equals to 1. First, x is equal to y is equals to 1. Now we have two equations, a is equals to by and b is equals to ax. In second equation, put the value of y. What is y? Y is 1. If we put 1 here, from this equation we get a is equals to b into 1. That is a is equals to b. A is equals to b. Or if we put the value of x in 1 means first equation, x is 1 here, a into 1 is 1. Again we get b is equals to a, b is equals to a means a is equals to b. Means if we consider x is equal to y is equals to 1, we get a is equals to b. Now consider second case, x is equal to y is equals to minus 1. If we consider second equation, a is equals to b into y, y is minus 1. B into minus 1 is a minus b. Means from second equation we get a is equals to minus b. Or if you put the value of x in first equation, what is x? X is minus 1. Here minus 1. B is equals to a into minus 1. That means b is equals to minus a. And b is equals to minus a again can be written as a is equals to minus b. Means we get two different conditions. If we consider x is equal to y is equal to 1, we get a is equals to b. For x is equal to y is equal to minus 1, we get a is equals to minus b. That means combining this, we have a is equals to plus or minus b. A is equals to plus or minus b. That means a divides b and b divides a implies a is equal to plus or minus b. Means at first we have taken a divides b and b divides a. Taking this, we are able to prove that a is equals to plus or minus b. Okay? Conversely, what happens if we consider a is equals to plus or minus b? If we consider a is equal to plus or minus b, then clearly A divides B and B divides A. Okay, this is the proof of fifth. Now in 6, if A divides B and B is not equal to 0, then we have to prove that modulus of A is less than or equal to modulus of B. What is given? A divides B. A divides B by the definition of divisibility implies that B is equals to A x for some integer x. Now taking modulus on both sides, we get mod B. Mod B is equals to mod AX. But using triangle inequality, modulus of A into B is greater than or equal to mod A into mod B. Using this, we get this is greater than or equal to mod A. That means mod B is greater than or equal to mod A into mod X. Okay. Again, it is given that B is not equal to 0. Since B is not equal to 0. Here, B is not equal to 0 means right hand side also not equal to 0. That is A into X is not equal to 0. Now, this is the product of two integers, but which is not equal to 0? That means any integer is not equal to 0. That means A is not equal to 0, X is also not equal to 0. That means B is not equal to 0 implies, from this implies X is also not equal to 0. Similarly, A is also not equal to 0. As X is not equal to 0, mod of X, modulus of X is greater than or equal to 1. Modulus of X is greater than or equal to 1. Okay. Now, as the modulus of X is greater than or equal to 1, the product of this must be, that means therefore mod B, this mod B is greater than or equal to mod A into mod X. Mod X. Here mod X is greater than or equal to 1. Therefore this product must be greater than or equal to mod A. Greater than or equal to mod A. That means mod B. This implies mod B is greater than or equal to mod A, or it can be rewritten as mod A is less than or equal to mod B. This is the required result. That means if A divides B and B is not equal to 0, then mod of A is less than or equal to mod of B. Then last property, we have proved just 6. Now proof of 7. The property is A divides B and A divides C. That means any one integer divide two different integers. Then we have to prove that A divides Bx plus Cy. That means that integer divides the linear combination of remaining two integers. What is given? A divides B. This is given. By the definition of divisibility, A divides B means B is equals to A. Already in this equation, x and y are taken. Instead of x and y, we shall consider another integer. B is equals to AR or some integer R. Second, A divides C. A divides C by the definition of divisibility, which implies C is equals to A into some another integer. We shall consider this as a S. Means A divides B is equal to B is equal to AR for some integer R. A divides C implies C is equals to AS for some integer S. Then we want to prove that A divides BX plus CY. We want a linear combination BX plus CY. To obtain the BX plus CY, multiply this first equation by X and second by Y and add these two. Means multiplying first by X, second by Y and adding, we get BX plus CY. This is left hand side. Multiplying by X, it will become BX. Multiplying by Y, it will become CY. And adding, we get BX plus CY is equals to, this will become ARX plus ASY. And therefore, BX plus CY is equals to, from these take A common, it can be done as A into RX plus SY. Now the quantity inside bracket is a new integer because X, Y, R, S, all these are integers. Therefore this product is an integer, this product is also integer, and the sum of two integer is again an integer. That means we get BX plus CY is equals to A into some other integer. That means this implies A divides BX plus CY for some integers X and Y. Okay, this is a proof of 7th. These are some properties.